Tonight, we are going to explore a structure that defies every human concept of size and distance. Imagine an entity so massive that its weight is 200 quadrillion times that of our Sun. If you tried to count to that number, one digit every second, it would take you 6.3 billion years, a span of time longer than the Earth has even existed. How can something so impossibly large exist within our reality? And what does its presence reveal about the true nature of the cosmos we call home? To understand this, we must first look at the world we know. Think about your house. The average American home is roughly 2,500 square feet, a space you can walk across in just 30 seconds. It is a scale your brain understands because you experience it every day. But as we step outside, the ladder of scale begins to stretch. A football field is 360 feet long. A mile is 5,280 feet. These are substantial distances, yet they still feel achievable. Now, look toward the sky. The moon sits approximately 238,855 miles away. When the Apollo astronauts made that journey, they traveled 50 times faster than a commercial airplane, yet it still took them 3 full days of continuous travel to arrive. Our own star, the Sun, is 93 million miles away. If you could somehow drive there at highway speeds of 65 miles per hour without ever stopping, the journey would take 163 years. You would have to pass the steering wheel to your children, and they to theirs, for several generations before the car finally reached its destination. Compared to the scale of what lies ahead, these distances are nothing more than a single grain of sand on a vast beach. We are about to climb a ladder where each new rung makes the previous one look microscopic. At these staggering scales, miles become uselessly small. To measure the gaps between worlds, astronomers rely on light. Light is the fastest thing in existence, traveling at a staggering 186,282 miles every single second. When you flip a switch in your room, the light seems to appear instantly because the distance is so short, but across the void of space, even light takes time to travel. When you look at our Sun, you are not seeing it as it is right now. You are seeing light that left its surface 8 minutes and 20 seconds ago. If the Sun were to suddenly vanish, we would continue to see it shining in our sky for more than 8 minutes before the darkness reached us. Because of these vast reaches, we use a unit called a light year. Despite the name, a light year is not a measurement of time, but a measurement of distance, the distance light travels in 1 full year. That distance is approximately 5.88 trillion miles. To put this in perspective, our nearest stellar neighbor beyond the Sun is a small red dwarf star called Proxima Centauri. It sits 4.24 light years away. This means the light hitting your eyes from that star tonight has been traveling through the freezing darkness of space for over 4 years, covering nearly 25 trillion miles just to reach you. Within a sphere roughly 32 light years across, there are approximately 50 stellar systems. This is our local stellar neighborhood. In human terms, it is unfathomably large. But in the grand design of the universe, this entire region is effectively microscopic. We are still just standing on the front porch of our own galaxy. The Milky Way galaxy is our home, a vast spiral of light that stretches roughly 100,000 light years across. To grasp that distance, consider that our galaxy is about 23,500 times wider than the distance to our nearest neighboring star. Within this immense structure, there are anywhere from 100 billion to 400 billion stars, each a massive ball of hydrogen undergoing nuclear fusion, and many likely hosting their own systems of planets. Our solar system is tucked away in one of the spiral arms, about 26,000 light years from the galactic center. When you look up and see that faint, misty band of light arching across a dark sky, you are looking at our galaxy edge on. You are witnessing the combined glow of hundreds of billions of stars, so far away that their individual lights blur together. Even at this scale, everything is in motion. Our Sun orbits the center of the Milky Way at a staggering speed of 515,000 miles per hour. Yet, the galaxy is so vast that even at this incredible pace, it takes between 225 million and 250 million years to complete a single orbit. The last time our solar system was in this exact spot in the galaxy, dinosaurs had not even evolved yet. Since our last lap, The dinosaurs rose to dominance, ruled for over 160 million years, and when extinct, mammals took over, humans evolved, and we finally built the technology to look back at the stars in all of human history. We have only just completed a single lap around our cosmic home. As vast as the Milky Way is, it does not exist in isolation. Our galaxy is part of a small cosmic neighborhood known as the local group, a collection of more than 80 known galaxies. The three largest members of this group are the Milky Way, the Triangulum Galaxy, and the massive Andromeda Galaxy. Andromeda is located approximately 2,537,000 light-years away. On a truly dark night, you can see it with your naked eye, a faint, fuzzy patch of light. But when you look at it, you are looking deep into the past. The light hitting your eyes right now began its journey toward Earth over 2.5 million years ago. When those photons first left Andromeda, modern humans had not yet evolved. Everything we consider to be human history has occurred in the time it took for that light to cross the void to reach you. The local group itself spans about 10 million light-years across, which is 100 times the diameter of our own galaxy. Yet, in the grand architecture of the universe, even this massive collection of galaxies is considered a tiny, localized structure. We are merely one small part of a much larger cosmic hierarchy. As we continue to pull our perspective back, the familiar boundaries of the local group begin to fade into the background. We are now entering a realm where galaxies are no longer individual islands, but are part of a massive, gravitationally bound collective known as the Virgo supercluster. This structure is a staggering assembly that contains at least 100 distinct galaxy groups and clusters, all woven together by the invisible threads of gravity. To imagine the scale of the Virgo supercluster, you must envision a region of space stretching 110 million light-years across. For most of our modern history, astronomers believed this was the final rung on the ladder, the largest possible neighborhood we could call home. It was a structure so vast that it seemed to define the very limits of cosmic organization. But in 2014, a groundbreaking discovery fundamentally redefined our cosmic address. Astronomers realized that the Virgo supercluster, as grand as it is merely a single lobe of an even more colossal structure, Laniakea. The name, drawn from the Hawaiian language, translates to immense heaven. It is a title that feels almost too small for the reality it describes. Laniakea is a cosmic watershed, a territory of the universe that encompasses roughly 100,000 galaxies and spans an unbelievable 520 million light-years. To help your mind grasp this scale, consider a simple comparison. If our entire Milky Way galaxy with its hundreds of billions of stars were the size of a single silver quarter, Laniakea would be the size of the entire United States. What makes Laniakea truly remarkable is not just the count of its galaxies, but the way they move. Within this immense heaven, galaxies are not drifting aimlessly. Instead, they are all flowing like water in a river toward a mysterious region known as the Great Attractor. This gravitational anomaly, located about 250 million light-years away in the direction of the Centaurus constellation, acts as the center of gravity for our entire cosmic continent. Every galaxy we have ever seen, every star we have ever named, is part of this silent, majestic migration across the deep. It is a thought that humbles the soul. We live our lives on a small planet, orbiting a single star, in a spiral arm of a galaxy that is just one of 100,000 others, all being pulled toward an invisible destination in the dark. And yet, as massive as Laniakea is, it is only the beginning of our story. As we venture beyond the boundaries of Laniakea, we must confront a truth that challenges our very understanding of order. When we gaze into the furthest reaches of space, we find that the universe is not a chaotic, random scattering of matter, nor is it a simple collection of galaxies drifting like confetti. Instead, the cosmos is organized into an incredibly intricate, three-dimensional architecture that scientists call the cosmic web. Imagine, if you will, a titanic spiderweb stretching across the entire observable universe. The glowing strands of this web are known as filaments, and they are the true highways of the cosmos. These filaments are composed of gas, dark matter, and entire clusters of galaxies, all strung together like luminous beads on a cosmic necklace. Where these massive strands intersect, They form the great cities of the universe, massive galaxy clusters containing thousands of individual galaxies. Between these strands lie the voids, enormous, hauntingly empty regions where almost nothing exists. The story of how this web came to be is a story that spans 13.8 billion years. Shortly after the Big Bang, the universe was nearly smooth, but it was not perfect. There were tiny, almost imperceptible variations in the density of matter, differences of only about 1 part in 100,000. In the silence of the early universe, gravity began to act upon these microscopic seeds. Over eons, the regions that were slightly denser pulled in more matter, growing even denser and stronger. Meanwhile, the less dense regions were slowly emptied as their matter was drawn toward the growing filaments. This grand design is held together by forces we are only beginning to comprehend. The visible matter we see, the stars, the planets, and everything we can touch, accounts for only about 5% of the universe. The rest is hidden in the shadows. Roughly 27% of the universe is made of dark matter, an invisible substance that acts as the scaffolding upon which all visible light is hung, and driving the entire web apart. Accelerating the expansion of space itself is dark energy, which makes up a staggering 68% of the cosmos. A single filament within this web can be hundreds of millions of light years long. But as vast as these filaments are, they are not the largest structures we have discovered. In 1989, astronomers Margaret Geller and John Hucra were mapping the positions of galaxies when they encountered something that shocked the scientific community. They found a massive sheet of galaxies, a structure they named the CFA2 Great Wall. It stretched 500 million light-years in length and 300 million light-years in width. This was only the beginning of our realization of just how large the universe's walls could be. In 2003, the Sloan Great Wall was discovered, a structure so immense that it stretches 1.37 billion light-years from end to end. To travel across its length, even light itself would need 1.37 billion years. We are no longer talking about neighborhoods or even continents. We are talking about the very fabric of reality, woven together on a scale that humbles the imagination. As we push our gaze even further into the abyss, the structures we encounter begin to defy not just our vision, but the very laws of physics we once thought were absolute. We are now venturing into a territory where even the term supercluster feels insufficient to describe the sheer majesty of what astronomers are finding in the deep. This is a realm where the universe seems to have forgotten its sense of modesty, building walls of light that stretch across billions of years of history. In 2017, a team of astronomers looking deep into the southern sky unveiled the Saraswati supercluster. This titanic structure is an almost incomprehensible wall of matter, stretching 652 million light-years from one end to the other. Within its boundaries, at least 400 galaxies are arranged in a dense wall-like formation, each galaxy hosting hundreds of billions of suns. To find this massive collective, we must look 4 billion light-years into the past. When the light we see from Saraswati today first began its journey toward Earth, our world was still in its infancy, a volcanic landscape where life had only just begun to stir. It is a haunting thought that while our planet was evolving, this massive cosmic wall was already standing in the dark, waiting for us to discover it. But the universe has a way of hiding its largest secrets in plain sight. In 2020, astronomers discovered the South Pole Wall. This is a massive filament of galaxies that stretches at least 1.4 billion light-years across the cosmos. What makes this discovery so remarkable, and perhaps a bit unsettling, is that it sits directly behind the plane of our own Milky Way galaxy. For decades, it remained invisible to us, tucked away in what astronomers call the zone of avoidance. The thick clouds of gas and dust from our own stellar home blocked our view of a structure that is 14,000 times wider than the Milky Way itself. It serves as a humbling reminder that even as we map the most distant reaches of space, there are still giants lurking in our own cosmic backyard, obscured by the very light of the stars we call our own. For many years, one structure reigned supreme in the debates of the scientific community, the Hercules Corona Borealis Great Wall. Discovered in 2013 through the analysis of powerful gamma-ray bursts, it appeared to be a titan beyond all others, spanning an unbelievable 10 billion light-years across. If this were a single, connected structure, it would occupy a significant fraction of the entire observable universe. However, this giant has always been shrouded in controversy. Many scientists have questioned whether it is truly one coherent object or simply a statistical illusion, a series of separate, smaller structures that only happen to look aligned from our specific perspective on Earth. For over a decade, the record for the largest thing in existence was a matter of intense and unsettled debate. That debate finally found its answer in early 2025. While the world went about its daily concerns, a discovery was made that officially settled the question of what holds the record for the largest confirmed coherent structure in the observable universe. It is a structure known simply as Quipu. It is here that our ladder of scale reaches its final, most breathtaking rung. In the quiet early months of 2025, while humanity was occupied with its daily terrestrial concerns, a team of astronomers made a discovery that would change our understanding of the universe forever. They found a structure so massive, so intricate, and so undeniably coherent that it settled the long-standing debate over the largest thing in existence. They named it Quipu. The name is as poetic as the structure is terrifying. In the ancient world, the Incan Empire did not use a written alphabet as we do today. Instead, they utilized a complex system of knotted cords, known as a quipu, to record vast amounts of information and history. When astronomers looked at their data, they saw a cosmic reflection of this ancient art. They saw a complex network of interconnected threads of matter, where massive galaxy clusters form the knots along the long, dark cords of the cosmic web. It is a fitting name for a structure that seems to hold the very history of the universe within its knots. To understand the sheer magnitude of Quipu, we must return to the number that breaks the mind its mass. Quipu is estimated to weigh 200 quadrillion times the mass of our own sun. Let that number settle in your thoughts for a moment. 200 quadrillion solar masses. If you were to sit down and begin counting to that number, 1, 2, 3, at a rate of one number every single second without ever stopping for food or sleep, it would take you 6.3 billion years to finish. By the time you reached the final number, our sun would have died, and the Earth would have long since become an uninhabitable cinder. We are not just talking about a large object. We are talking about a structure that weighs more than the collective imagination of our species can hold. What makes Quipu particularly significant to the scientific community is its confirmation as a single, coherent structure. Unlike the controversial Hercules Corona Borealis Great Wall, which was identified through indirect statistical patterns and remains a subject of intense skepticism, Quipu was detected through the direct observation of X-ray emissions deep in the reaches of space. The galaxy clusters within Quipu are filled with gas that has been heated to millions of degrees by the immense gravitational collapse that formed them. This gas is so hot that it glows with X-ray light, which our satellites can detect from Earth. These X-ray patterns reveal the physical bridges of hot gas that connect one cluster to another, proving that they are not just coincidentally aligned in our line of sight, but are gravitationally bound into a single titanic system. Within Quipu, there are 68 of these massive galaxy clusters. They are not scattered randomly. They are meticulously arranged along filaments of dark matter that stretch between them, forming the largest skeleton ever discovered in the observable universe. Each one of these 68 knots is itself a gargantuan city of light, containing hundreds or even thousands of galaxies, each home to trillions of stars. However, the existence of Quipu does more than just break records. It challenges the very foundation of how we believe the universe evolved. For nearly a century, our understanding of the cosmos has been built upon the cosmological principle. This principle suggests that at the largest scales, the universe is homogeneous and isotropic. It assumes that if you zoom out far enough, the universe should look essentially the same in every direction, averaging out into a uniform smoothness without any preferred directions or excessively large structures. This idea is supported by the afterglow of the Big Bang, which appears remarkably uniform across the entire sky. Quipu pushes against the absolute limits of this principle. There is a theoretical limit to how large a structure can grow, within the 13.8 billion year history of the universe, because gravity can only pull matter together so fast. Quipu is so massive and so sprawling that it forces us to ask, how did it have time to form? At what point does the universe stop being smooth and start being dominated by these impossible giants? Scientists are now exploring several radical possibilities. Perhaps our models of how structures form need a complete refinement, perhaps dark matter. The invisible scaffolding of the web behaves much differently at these extreme scales than we ever expected. Or, more excitingly, perhaps there is new physics at play, a fundamental law of the universe that we have not yet discovered. The honest truth is that we do not fully know. Quipu remains a mystery, a silent giant that stands as a reminder that the universe is far larger, far older in its complexity, and far stranger than we ever dared to imagine. To truly appreciate the magnitude of a structure like Quipu, we must look beyond its sheer size and venture into the environments that make it up. Each of the 68 galaxy clusters that form the knots of Quipu is a titanic city of light, holding thousands of galaxies within its gravitational grip. But as we zoom into these cosmic metropolises, we find that the visible galaxies, the glowing spirals and ellipticals we admire, are merely the surface of a much deeper and more violent reality. These clusters are defined by two massive, shared resources: a sea of superheated gas and an invisible scaffolding of dark matter. The space between the galaxies in a cluster is not empty. It is filled with the intra-cluster medium, a reservoir of primordial gas, mostly hydrogen and helium, left over from the very birth of the universe. This gas was never part of a star or a planet. Instead, it fell into the cluster's immense gravitational well and was heated to temperatures of 100 million degrees by the sheer force of its own compression. At these temperatures, the gas becomes a plasma so hot that it glows with high-energy X-rays, invisible to our eyes but glaringly bright to our space-based telescopes. In a typical galaxy cluster, this hot gas contains far more mass than all the visible stars in all the galaxies combined. If you were to weigh every sun in a cluster and compare it to the weight of the gas floating between them, the gas would win by a factor of 5 or 6. Yet, even this fiery ocean of plasma is not the dominant player. The true master of the cluster is dark matter. Dark matter accounts for a staggering 85% of the total mass of a galaxy cluster. It provides the invisible gravitational framework that prevents the hot gas from dissipating into the void and keeps the galaxies from drifting away. We call it dark because it does not emit, absorb, or reflect light. It is a ghost that we can only detect through the pull it exerts on the things we can see. Our understanding of this invisible force began in the 1930s when the astronomer Fritz Zwicky studied the Coma cluster. He noticed that the galaxies were orbiting the cluster's center far too quickly. They were moving at speeds that should have sent them flying out into deep space. Either the laws of physics were wrong, or there was a massive amount of invisible matter providing the extra gravity needed to hold the cluster together. Zwicky was right. Dark matter is the scaffolding upon which the entire cosmic web, including the massive Quipu, is built. What is this mysterious substance? Astronomers have proposed several candidates, from weakly interacting massive particles, known as WIMPs, to extremely light particles called axions. Some suggest it could be primordial black holes, formed in the earliest seconds of the Big Bang, or even a hypothetical type of particle called a sterile neutrino. Despite decades of searching with detectors buried deep underground to shield them from cosmic rays, we have yet to capture a single particle of dark matter. It remains one of the deepest and most haunting mysteries in all of science. We see the clearest proof of dark matter's nature when galaxy clusters collide, events that are among the most energetic since the Big Bang itself. Because dark matter is collisionless. When two clusters smash into each other, the dark matter halos and the galaxies pass right through one another, like two swarms of ghosts. The hot gas, however, is a different story. As the clusters collide, their gas clouds smash into each other, creating titanic shock waves that slow the gas down, causing it to lag behind the rest of the cluster. The most famous example of this is the Bullet cluster. By using gravitational lensing to map the mass and X-ray telescopes to map the gas, astronomers found that the mass is centered where the galaxies are, not where the gas is. This smoking gun proves that most of the matter in a cluster is dark, and does not interact with anything except through gravity. Within Quipu, these collisions and mergers are happening across hundreds of millions of light years, slowly assembling the 68 knots into the singular structure we see today. But these clusters also possess a heart, a central engine that regulates their very existence. At the center of nearly every large galaxy in these clusters sits a supermassive black hole, an object millions or even billions of times the mass of our Sun. When matter falls into these black holes, they launch jets of particles at nearly the speed of light, punching enormous holes into the surrounding hot gas and creating cavities that span millions of light years. These black holes act as a cosmic thermostat. Normally, the hot gas in a cluster should cool down and collapse to form new stars, but the energy from the black hole's jets heats the gas back up, preventing it from cooling and keeping the cluster in a state of balance for billions of years. In Quipu, 68 of these central engines are pulsing, regulating the birth of stars across a significant fraction of the observable universe. It is a system of systems, a delicate dance of heat, light, and invisible gravity on a scale that humbles the stars themselves. As we stand in awe of the colossal, glowing filaments of Quipu, we must also confront the terrifying beauty of what lies between them. To truly understand the structure of the universe, we must look into the great nothingness. These are the cosmic voids, the least dense and most desolate regions in all of existence. While the name might suggest a complete vacuum, these voids are not entirely empty. Even in the deepest reaches of the dark, there is a thin, ghostly scattering of matter, halos of dark matter, lonely clouds of gas, and a few isolated galaxies drifting like shipwrecked survivors in a vast black ocean. However, compared to the crowded cities of light that make up the filaments and clusters of Quipu, these voids are effectively empty. In these regions, the density of matter drops to a staggering 1/10 or even 1/20th of the cosmic average. One of the most famous examples of this desolation is known as the Bodi's Void, often called the Great Void. It is a spherical expanse of nothingness, measuring approximately 330 million light-years across. To put its emptiness into perspective, consider this in a region of that size elsewhere in the cosmic web. You would expect to find at least 2,000 galaxies. In the Bodi's Void, astronomers have discovered only about 60. Imagine for a moment what it would be like to exist inside such a place. Imagine a civilization evolving on a planet orbiting a star within one of those 60 lonely galaxies. When their astronomers looked up at the night sky, they would see their own galaxy stretching across the dark. But beyond it, they would see almost nothing. The distant, comforting glow of the cosmic web would be too far away to detect with the naked eye. Their cosmic horizon would feel much smaller, much more confining than our own. Without the context of a surrounding universe, they might very well conclude that their single galaxy was the only thing in existence, an island of matter floating in an infinite, eternal emptiness. The existence of these voids is just as vital to our understanding of the universe as the existence of the great walls and filaments. They are two sides of the same coin. Over 13.8 billion years, gravity acted as a cosmic sculptor, pulling matter away from these regions and funneling it into the dense structures of the web. The voids represent the places where the universe has been hollowed out, evacuated to build the giants like Quipu. The cosmic web is defined not just by its fullness, but by the staggering scale of its emptiness. To truly grasp the staggering scale of the largest structure in the cosmos, we must leave behind the safety of our world and embark on a journey that is, by every law of physics, impossible. Picture yourself boarding a spacecraft of unimaginable power, one capable of accelerating instantly to the speed of light. You position your vessel at the very edge of Quipu, staring out across a horizon that stretches 1.4 billion light-years into the distance. As you begin your crossing, the familiar stars of our neighborhood vanish, and you are confronted with the true skeleton of the universe. For the first million years of your journey, you travel through regions of haunting sparseness. Quipu is not a solid wall, but a network of structures within structures. Occasionally, a lone spiral galaxy drifts past your viewport, a brilliant island of light containing billions of stars. But for most of this initial trek, there is only the vast emptiness, the thin haze of primordial gas, and the nearly invisible scaffolding of dark matter. You are flying through the ocean, between the islands of the cosmic web, After 10 million years have passed, you encounter your first major landmark, a titanic galaxy cluster. Suddenly, the darkness is filled with hundreds of galaxies spread across millions of light years. They are embedded in a cloud of gas so hot that it glows with the fierce energy of X-rays. Over the next few million years, you glide through this city of light, watching hundreds of billions of suns drift past like glowing embers. Then, you emerge back into the relatively empty space of the filaments, long, thin bridges of matter that stretch between the massive clusters. When your journey reaches the 100 million year mark, you have crossed less than a tenth of the total distance of Quipu. If you could look back at Earth, the world you left behind would be unrecognizable. 100 million years is enough time for the very face of a planet to change. Continents have shifted their positions. Mountain ranges have risen from the Earth and been eroded back into dust. And entire groups of species have evolved, flourished, and vanished into extinction. And yet, for you, the journey through Quipu has only just begun. You continue onward, passing cluster after cluster and filament after filament. The structure seems endless, a repeating pattern of cosmic organization. Each cluster you encounter is unique, possessing its own history of formation, its own patterns of superheated gas, and its own collection of diverse galaxies. You could spend thousands of years studying the secrets of just one of these clusters and still not understand its full complexity. By the time you are 500 million years into your flight, you have crossed roughly 1/3 of Quipu. On the Earth you once knew, 500 million years is enough time for almost anything to occur. It is a span of time that could see complex multicellular life evolving for the very first time, or perhaps life going extinct and starting over from the shadows. During this era, the planet might have been struck by massive asteroids, frozen solid in a snowball Earth event, or baked by cataclysmic volcanic eruptions. Time, on a planetary scale, has moved through entire eras, while you have merely moved through a fraction of this one cosmic structure. After 1 billion years of travel at the speed of light, you are finally approaching the far side of Quipu. But the solar system you call home is now a different place. Our star has aged noticeably, burning through its hydrogen fuel and growing significantly brighter than the day you left. On Earth, the oceans may be beginning to evaporate under the increasing heat of the sun. The delicate conditions that allowed human life to flourish are slowly fading into history. Finally, after 1.4 billion years of continuous travel, you emerge from the far side of Quipu. Behind you lies the largest known coherent structure in the observable universe, a network containing billions of galaxies, trillions upon trillions of stars, and countless hidden worlds. Ahead of you lies the rest of the cosmic web, more filaments, more voids, and structures that are perhaps even larger, still waiting in the dark to be discovered. This thought experiment illustrates the true meaning of a distance of 1.4 billion light-years. While no object with mass can ever achieve the speed of light, and 1.4 billion years is a span of time beyond human comprehension. Imagining this journey helps us understand our place within the grand design. We are small, our lives are brief, and our world is fragile. Yet, we are the only part of this vast system that has developed the curiosity and the capability to map its structure and wonder about its origins. As we stand at the threshold of our final discovery, we must zoom out one last time to consider the stage upon which Quipu exists, the observable universe as a whole. To our eyes, this is a vast sphere centered on Earth, reaching out with a radius of approximately 46.5 billion light-years. You might wonder how this is possible when the universe is only 13.8 billion years old. The answer lies in the restless nature of space itself, which has been expanding the entire time light has been traveling toward our telescopes. When we look at a distant galaxy whose light took 13 billion years to reach us, that galaxy is no longer where it was. The expansion of the cosmos has carried it much farther away in the intervening eons. Within this observable sphere, there are approximately 2 trillion galaxies, each teeming with hundreds of billions of stars. We now estimate that there are at least 200 billion trillion stars in the observable universe, and likely even more planets orbiting them. Yet, even this staggering reality is not the entire story. The observable universe is merely the part we can see, limited by the speed of light and the age of the cosmos. Beyond our cosmic horizon, there is almost certainly more universe regions so distant that their light has not yet had time to reach us and, due to the accelerating expansion of space, Likely never will. Whether the universe is truly infinite or merely finite but unbounded, we may never know for certain. This means that as massive as Quipu is, it might be small compared to structures that exist beyond the reach of our vision. However, the clock is ticking for the great cosmic web. The universe is not just expanding, that expansion is accelerating, driven by the mysterious force of dark energy. Distant galaxies are receding from us at ever-increasing rates as space stretches between us. For structures as far away as the edges of Quipu, the space between us is expanding so rapidly that the distance grows faster than light can traverse it. This has profound and melancholy implications for the future of the universe's largest residents. Dark energy is slowly but surely winning its ancient battle against gravity. As the eons pass, the growth of large-scale structures will slow and eventually stop altogether. The cosmic web we see today will one day freeze into its final configuration, unable to pull more matter into its filaments. Tens of billions of years from now, Quipu will become more isolated. The connections between its 68 clusters may thin or break entirely, leaving the structure to persist as a lonely island surrounded by an ever-expanding, empty void. In the very far future, even the light of the stars will begin to fade. Our own sun will exhaust its fuel in about 5 billion years, though Earth will become uninhabitable long before that as the star gradually brightens. Eventually, the last red dwarfs will flicker out, and even the most massive black holes will slowly evaporate through Hawking radiation. Trillions of years from now, the universe may become a cold, dark, and nearly empty void where the cosmic web is nothing more than a distant memory. But that is a future too distant to dampen the wonder of the present. For now, the universe is full of light, structure, and life. When we contemplate a giant like Quipu, we are confronting the very limits of human comprehension. Our brains, evolved for survival on a small planet, are not naturally designed to grasp structures spanning billions of light years, yet we have found a way to understand them through the language of mathematics. We have built supercomputers to simulate the birth of the web and telescopes to map its furthest reaches. From a cosmic perspective, a human life is a brief flicker 80 or 90 years in a universe that is billions of years old. We exist for the blink of an eye on a tiny rock orbiting an ordinary star. But there is something remarkable about your existence. You are made of atoms forged in the hearts of dying stars billions of years ago. That matter was recycled through the cosmos, eventually finding its way into you. You are literally made of stardust. And because you possess a mind that can wonder, you are the universe's way of knowing itself. You have spent this time learning about a structure 1.4 billion light-years across, containing trillions of stars and countless worlds. You have contemplated distances that dwarf all human experience. That, in itself, is a profound achievement. The next time you look up at the night sky, remember that those points of light are not just stars. They are part of a galaxy, which is part of a cluster, which is part of a supercluster, all woven into the cosmic web that stretches across the observable universe. You are connected to all of it, subject to the same laws of physics and part of the same grand cosmic story. Every star you see has a story, whether it is a young star just forming or an old one nearing its end. Thank you for taking this journey with me through the deepest reaches of space. If you found value in this exploration of the largest things in existence, please consider liking this video and subscribing to the channel to help us keep making content like this. Remember, the universe is far larger and stranger than any of us can imagine. We are small, but we are infinitely curious and capable of wonder. Keep looking up, and never stop asking questions about the cosmos we call home.